2024 time zone 2 pivot to AHL. AHL. Question 12. It's the last question of the paper. So again, by tradition, it's either Maclaurin or differential equation. This time it's differential equation. Do an Euler method. So step size is pi over 12, so h is pi over 12. We start when x is 5 pi over 12, and we start from 4 pi over 4, which is 3 pi over 12. Okay, just 2 steps. I guess I can do that. So n, xn, yn, and fxn, yn. That's how I usually do it. F really means dy dx. So for this question, it would be root tangent plus y cosecant 2x. So make sure you calculate this in radian, otherwise everything will be all wrong. So the original step, xn is pi over 4, yn is also pi over 4, and h is pi over 12, I didn't write that. And fxn, so I need to calculate that. It's root tangent pi over 4 plus y, what's y? Also pi over 4. Cosecant is 1 over psi. 1 over psi. 2x, so 2 times pi over 4. So it's 1.78. Use the most decimal place possible. And then we need the formula for Euler method. I think it's provided in the formula booklet. To be something like y, f plus 1 equals yn plus h times of f, xn, yn. So, and xn plus 1 is simply xn plus h. So the first step, we have pi over 4 plus pi over 12, that's h, pi over 12 is h. Oh, pi over 3. What's y? It will be the previous y plus pi over 12 times this times fxn. 1.2528 1431. Then you substitute those values into f like this, except x is now this is actually a better way of doing this, which is typing this into the spreadsheet of your calculator. It's almost like you're using Excel and write a program, so it will automatically calculate it for you. In case you don't know that method exists, you really should figure it out. I'm not the best at programming, but YouTube Euler method on the model of your GDC, because it really depends on which GDC you have. That's why I'm not showing how you do it on mine. It wouldn't mean much for you, especially no one uses this GDC in real life. This is just a iPad calculator. So I didn't do it, but you really should learn that way. But just when you search, it has to be the way that use the spreadsheet. You cannot use the built-in function of Euler method of a calculator. That would be locked in an exam mode, so it wouldn't help you. Yeah, so really figure that out. Otherwise, because it's just this time there is only 2 steps. It has happened that you need to do maybe 5 steps, maybe 10 steps even. So it's really best if you know that way. Times f. I don't really need to type by myself, do I? It's 1.976. How many significant there were? 3 significant figure. 1.98. I hope I'm right. Okay, I'll check the marking scheme. It's right. Show that the derivative of half log cotangent is that should be straightforward. So it's half times ln differentiate ln is 1 over. Then chain rule times differentiate the inside. Differentiate cotangent is negative cosecant squared. Oh, it's not as straightforward as I thought. So it's negative over 2. Cotangent is cos alpha psi. Cosecant is 1 over psi squared. So psi x and the psi squared cancel out. So you have 2 cosine x sine x. Obviously that's doubling the formula for psi. So that's sine 2x. So that's negative cosecant 2x. Okay, nice and easy. Show that the square root of cot is an integrating factor. So they're nice. They tell you this differential equation is the type of integrating factor. So the integrating factor is e to the power of the integral of px. Px is the thing that is multiplied to y. So it's really negative cosecant 2x. But what is the integral of negative cosecant 2x? Well, from here we know if you integrate negative cosecant 2x, you get this. So it's half ln cot and then obviously we move the power inside the log, because then e and ln can cancel out. So you have cot x to the power of half, which is square root of cot. That's the integrating factor. And hence solve the differential equation. So after you find the integrating factor, you should just memorize the steps, right? You would multiply it through the whole differential equation. The reason is that the left-hand side would always collapse into the derivative of the integrating factor times y. You really should know why. If you don't know, you should learn the content. And if you want, you can watch my lectures to learn the content. We multiply them. Cotangent x times tangent x is 1, because cotangent is 1 over tangent. So root 1 is 1. So 1. So now it means if you differentiate this, you get 1. Therefore, the thing inside is really the integral of 1, which is x, plus c. So y is really x over cot x plus c over cot x. But cot is 1 over tangent. So if you over it, it becomes tangent. Plus c of tangent. Then we can find c. We know that when x is pi over 4, y is pi over 4. So we just sub it in. Tangent pi over 4 is 1. So this is 1. 1 times pi over 4 is pi over 4. You minus, you get 0. So c end up to be 0. So that's why the function is really just x times tangent x. Find the y coordinate. Now we know the actual solution. We can find the actual value. 5 pi over 12 times root tangent 5 pi over 12. It's what, 2.5288. Wow, that's off by crazy amount. Not even close. Well, the question actually admit why. Well, the question actually tell you it won't be a good approximation. So in exam, even if you found something quite off, you don't need to panic. The question is why though? Why would it be off by so much? They ask us to consider the gradient of the curve. I don't really know what that means. But it says to consider the gradient. The gradient of the curve is really dy dx. So they want us to consider this. Maybe not. Maybe we should actually differentiate this. What part are we doing? EII. What happens if we differentiate this? So it's product rule. So we differentiate the first thing, get 1, copy the second, plus copy the first, differentiate the second, so it's half tangent negative half times differentiate tangent, that's secant square. And then I guess I would try to plug in 5 pi over 12, see what would happen. This is obviously me guessing how to do it. Times 1 over 2 times, this is not easy to type, to the power of negative 1 over 2 times secant square, so that's 1 over, let me put times just in case, over secant is cosine squared, so it's cosine 5 pi over 12 squared. It's roughly 6.9, so roughly 7. I don't see why. I mean, that's quite big, but I was expecting something even bigger. What if we graph it? X times 1 over 2 times bracket tangent x to the power of negative 1 over 2 times 1 over cosine square. And we kind of want to know what happens when x is around pi over 4 to 5 pi over 12. But we'll make it wider, I guess. So instead of 5 pi over 12, maybe we'll 7 pi over 12. Make it wider so we can actually see. Why is the y value so big? Make it hollow, maybe? I'll change it. Confirm. Okay, that's probably better. Now what's 5 pi over 12, right? 5 pi over 12. So around here. So I'm guessing it's because x being 5 pi over 12 is quite close to a vertical asymptote, which means when you go near 5 pi over 12, suddenly the gradient would go up crazy fast. And Euler method is estimating by using the gradient of the previous point, right? So if your graph suddenly go up really, really fast, then Euler method won't be that accurate. But from the graph, it doesn't look that crazy. I guess because my scale is really crazy. What if I do this? Then I can't even see it. Like, where's 5 power 12 again? Yeah, so it's like when you go here, 5 power 12 is quite close to the vertical asymptote. That's the best reason I could thought of. So I think that's the answer. So we don't even need the value. It's because 5 power 12 is close to it's like, oh, we just say the gradient is increasing very rapidly around x being 5 power 12. That's probably my best answer. State why the approximation is less than the y coordinates. So the question is, why is our approximation less than the actual value? Well, the question is always because the original function is concave. Concave up, I think. Just to be sure, we graph it. So sine square root tangent x. Yep, so around there, it's concave up. It's because the original graph is concave up around x being 5 power 12. Right, because if your graph is concave up, remember Euler method is using a tangent to estimate the y value of the next point. So if your graph is concave up, you always increase more than the tangent line. So the estimation which use the tangent line would always be less than the actual function value. So that's a very common question. Just I is less common. By considering blah, deduce that the graph has a positive gradient when x is between 0 to power 2. Like, why would we do that? Like, I know the graph. I can like just graph the graph. Or I can actually differentiate the graph or something. Like, why why make us do this? But I guess we'll have to do what they say. So dy dx is actually root tangent x plus y cosec 2x. But we know y now. Y is really x root tangent x cosec 2x. Then what? I don't know. Well, when x is between 0 to power 2, tangent x is positive. So you can root it, right? It's possible to square root it. And the square root is always positive. So root tangent x is bigger than 0 anyway. Well, it could equal to 0. But not really. Tangent can't be 0 because x can't be 0. And then x is also bigger than 0 as x is between 0 to power 2. What about cosec 2x? Cosec 2x is really 1 over sine of 2x. But if x is between 0 to power 2, then 2x is between 0 to pi. From 0 to pi, sine is positive, so this is also positive. So pretty much everything here are positive. You have some positive stuff plus some positive stuff, so overall is positive. Therefore, dy dx is positive. Well, dy dx is gradient, right? So that's why we have positive gradient. Alright. Okay, I think that will do. Yeah, there's some tricky part at the end of question 12. Before that, it's kind of standard, right? Euler method and solving integration factor. They even tell you it's an integration factor, integrating factor, so it's not too hard. The tricky part probably only worth a few marks, so it's not too bad. So overall, the paper isn't too bad, I guess. It's just question 10 and 11 kind of it's quite annoying. Have some tricky stuff that could cost you some significant amount of marks. But after all, it's actual math, right? So have to contain a certain amount of challenge.